take us through it one after the other. So let's go through the question again. The question says a right cone and a cylindrical pipe intersect axially at right angles as shown. All right, we'll look at that again. Draw the complete elevation and plan, the curve of intersection of the pipe and cone, and C, the development of T with OS as same. There's always a same given in most WAEC questions, so you have to be careful. This is the same here. OS is the same. Okay, guys, I had to recreate the question so that we have a clear picture of what it will look like. This is what a typical WAEC question would look like. You'll be given a figure like this and asked to draw the curve of intersection, the complete plan, and all of that. Of course, looking at this dotted long dotted line here, the long dotted line indicates that it's a center line, and if it's a center line, that means the base is supposed to be round, which means we are dealing with a cone. And the base, of course, is going to extend this way, 60, and I can drag this one down. That way. This plan would need to make sure it's complete, drawing all center lines that are necessary and are a requirement according to WAEC standard. So we would have a center line here. Take it up. Okay, another center line here. All right, now we have a complete plan, but that's not all. Remember, we have an intersected cone here, and it has dimension 30. 30 is the diameter of the circular pipe, and the length here is 31. It may not appear 31 here, but then we're going to use steel construction lines to project from the top looking downwards. We know this edge would be viewed, this part would also be viewed, this point of intersection, the center line, would also be viewed, saying downward, and this edge would also be viewed. Three most important parts will be viewed downwards. All right, so we would replicate these points on the plan. Okay, here we go. We now have pipe U on the plan. Remember, the idea is whatever you do to the front elevation, try to replicate the same thing on the plan. That's what we're going to be doing all through curve. To represent what's happening, we're going to draw a semicircle from here to here. And remember, whatever you do in front elevation, make sure you replicate the same in the plan view. So we're going to do the same thing here in the plan view. So we have this, everything is coming out nice and cool, and we would continue in this manner. So the next thing to do is to divide this semicircle into 4 equal parts. All right, 4 equal parts. So I'm going to type in 4 here. If you're looking at the left bottom corner of my screen, you'll be seeing some of the numbers that I'm typing that appear there. So I have 4 divisions now. If you have a compass, you could place your compass, your cut here, place your compass here and cut here. The line drawn from that point to the center, okay, will pass through this division that I already have right here, and that will also pass through here. You have a division like this. So what's next is to actually run cutting planes through each point. And by cutting plane, I mean imaginary cutting planes, because you're still constructing. So it's going to be one cutting plane here, another cutting plane here, Uh, would I like to extend this because we're not done drawing yet. So extend this line, extend this line, extend this line, extend this line. We may have to trim them later. All right, the same thing that we've done here is what we're going to transfer down to the plan. Same thing, same thing. Yeah, right here. So run cutting planes here, same cutting planes there. So the next thing to do is to number these cutting planes so that we represent them appropriately, both in front elevation and on the plan. Okay, they've been numbered nicely. I would like us to look at the numbering. Look at the front elevation. We started with 0, 1, 2, back to 1, and then back to 0. But on the plan view, we have 2, 1, 0, 1, 2. That is because if you're looking in the front view, the top of the cylinder is going to appear 0. But if you're looking from the top view, that 0 is going to appear in the middle. And then this 2 becomes what you're going to see by the side, right? I hope this makes sense. Okay, so then this cutting planes from one through length, the cone has 2 through lengths. The 2 side lines are regarded as true lengths because any other line drawn somewhere here in the middle will not be regarded as true length because the cone is supposed to be circular, and when you turn anytime you turn that line and it rotates, this becomes a true length. But when it comes somewhere close to you, or the straight line that I'm saying, this axial line that I'm saying, cannot be regarded as true length because in another video we'll discuss that in detail. So from one true length to another true length and then projecting back to the plan. Remember, I said the business we're into is whatever we do in front elevation, we are running cutting planes in front elevation, we've run cutting planes in the front elevation too. Now we are going to extend this cutting plane to touch the true length here, and that true length we're going to trace its path on the plan. So let's do that quickly. Here, all of these are going to be extended. So this point would have an address on the plan. So let's check their addresses. We're starting with point 0 at the top. We have it here. We have point 1 followed by point 2, followed by point 1 again, and then the last one followed by point 0. So you see all of them passing through these points in the plan view. So we'll look at areas that they are cutting and mimic this part in a circular form, because this part will not appear the way they are anymore. They will go in this manner, in a circular part. So let's draw all the points from 0. I'm addressing 0 first. 0 will go around, and I'll stop here because that's where the curve is probably supposed to stop. If we have double curves, I'll have to go around a full circle. This way. I'd like you to check, I'm not just drawing circles. This first circle, this circle, the inner one, is actually touching this line here. And if you check the address from where we're coming from, it's tracing it back. So we're starting from 0, hitting this point, coming back, and then touching this point, and then going back to where it came from. Okay, that's going to give us the address of what we're doing. So let's do the next one. If you check the second one, here, I'm cutting 1 here, and I'm also cutting 1 here. If you trace this one back, you'll be somewhere around here. Okay, so that's what we're doing. So let's go ahead from the center, put your compass on O, extend it to 2, and let it go around touching 2. So we have this touching 2 here and this touching 2 here. We'll address all those issues later. It's pretty much close to 1, so we have to be careful. And then I'm going back to 1, going around and touching this. The last one is the 0 at the bottom. So 0 at the bottom, we're going to go around. So here we're starting with line 1, line 0. we'll look at where line 0 is cutting. It's cutting this here. So we'll have to project this line back to line 0. Let's see where the address of it will be in the front elevation. So 0, you're here. 0. See, 0 is tracing it back on the curve on this line 0 in the front elevation. Look at it. Exactly where it should be. So we have that line 0. We would look at another point. But let me show you. This is line 1. We'll look at it. We'll trace line 1 on the plan. Look at where line 1 cuts. Line 1 is cutting line 1 here. And it's also cutting line 1 here. This cutting plane 1 here. So we would produce the vertical projection of that line upwards. This is the line touching here and also touching here. And it is intersecting. If you trace up, it is intersecting the line here, this plane. Got it? Intersecting here. So we have a point there. Similarly, we shall do that for the line in the middle, which is line 2. Line 2 is touching line 2 here. It's line 2 now. I have to zoom this very close to the other line. Touching line 2 here. And it's also touching line 2 here. Right. The next line is line 1. We can see it's touching line 1 here. Bring this one close. You can see it's touching line 1 here. And the last one is 0. 0. You have to trace the curve. 0 is on 0. So we have 0 already. So we don't have to draw that. 0 is going back to 0. You can see 0 here. Good. Yeah. So pretty much everything we need, but we would have to draw the curve of intersection on the plan. We join all the points that we have here, and we also join all the points that we have here. Trim all the lines out and work this nice and cool. Okay, taking this line out. From the plan view, intersect is this line 1. And if we trace 2, we find 2 here. Let's see. 2 is this offset of the line that I'm seeing here. This one. I'm going to trace this up and find it right here. Good. This is clear. We can see 1 here. And 0. We can see 0 here. So this is the curve of intersection that we're looking for. I'm going to highlight that the blue line so that you look at it differently. That's the curve of intersection that we're looking for. So what's next is to trace the same point on the plan view, because we can actually see this line on the plan view. So we do same. Remember, the idea is whatever is. So let's start again. Starting at 0. Looking at the point where this 1 intersects 1. I think it's here. Yeah, right here. Then I have 2. I hope I'm correct. Yeah, I have 2 there. And going up, I have 1. And here I have 0. Going into this inner line, I have 1. Going on the outside, I have to be careful with this line, these 2 lines. I have 2 there. I have back here 1. And I'm going to return to 0. All right. So that's where we are at. This curve you see in the elevation, this one, is the same curve. If I'm looking from the top, I'll see this part from this part, and the other part that I'm not seeing the other on the other side, on the flip side of the cone. All right. So in the plan view, because I'm looking at the top, I'll be able to see this whole thing. However, the pipe goes round downtown, so I'm not going to see this part though. The part below, zero. The zero down, I'm not going to see this zero. This zero down, I'm not going to see it, but I'll represent it with a dotted line. So I'm going to do that later. You find out why we're doing that, and let's carry on. I just wanted to show you the lines are still there, but this line, this one down, it's going to be represented with a dotted line, just to give some respect to it. What do we have again? Yeah, this is complete. The next thing to do, which is independent of what is happening here, is the except that we're showing this whole of intersection is the development. So we'll do that shortly. But let's finish up this out. Okay, we're almost done. And what's next for us to do is to draw the development of T with OS as same. So we are looking at O prime S as seen and opening up the cone in that manner. So we have the curve intersection here. We have the curve represented in the plan view. We have the cone also represented in plan view. We have the pipe U also represented in plan view. So what's next is to draw the development of the cone. So to do that, we are going to open up the cone using O prime as the center and S as the radius. Okay, see my action? I'm opening it up from here, opening up this way. But now the question comes, how long is this arc, this very arc, supposed to be? How long that arc is supposed to be is dependent on the length of this, which becomes our new radius. Here is 74.3 with respect to the diameter of the cone, or the radius of the cone too. The radius of the cone here in this case is going to be 30. We have a radius here which is 74, approximately 75, whichever one you want to take, or 74, whatever. So I think I'm using 74 here. So I have R30 theta here. The angle subtended by this cone is going to be referred to as theta. And there's a little calculation here that I did. Development with OS is same. L, which is the length of this arc, is giving us 2 pi r times 360 over times theta over 360. If you do that calculation, knowing that the base of the cone is also 2 pi r, if you equate L with this, 2 pi cancels out, and what you're left with is r30, r74, and then this puts theta, make theta the substitute formula. You have 146 angle. So we are going to calculate 146 angle here using your protractor. You can actually determine that, or we use the measurement here to determine 146 angle. That we can do. But if we use 2 pi r, we are going to get a value that would give us this. So we'll do that quickly. Another alternative is to divide the base of the circle of the cone, this circle, into 8 equal parts, and then take one division of that part, cut it along this cone until you get to 8 divisions as well. That's how you can actually do it. 2 ways. You either use the angle using a protractor, or you divide the base of the cone into 8 equal halves and use one part of that half and divide through the lines. Okay. Okay, the 8 point is exactly here. 1, 2, 3, 4, 5, 6, 7, up to 8 here. What's probably appropriate and quick would be to simply measure the angle with your protractor and then get the extreme parts of the arc, which is subtended by these two radii. Let's measure the angle to see what we have. Measure the angle subtended by the arc. You see exactly showing angle 146 right here. Yeah, we also see it here 146. So that's good. We have 146. Then keep it that way. 146. Good. Now let's start tracing points. And how we trace this point quickly is this. The seam, it's here. I open up this from here. How long will I travel to get to 0? That's half of the cone. And half of the cone will be half of this arc. Half the cone will be half of this arc. So to get half of that, you take 146 and divide it by 2. You get a straight line through and mark that point to be 0. This is what I mean. So how the cone is going to be from here to one of the arcs in the middle, right there. And we can call that reference point, point 0. That reference point is point 0. Where does this point 0 lie? This same point 0 is the same point 0 that we have here. Okay. Okay. This is where we stopped in the development of an intersected cone by a cylinder U and T. Our challenge was in actually developing this ellipse, so to speak. May not be an ellipse, but an oval shape or an oval hole here. And I couldn't show it live because it was actually difficult to pull up using AutoCAD, but I will explain that in a bit. So to trace all the points, we have traced all the points from PO hitting the true length, and then this way, P1 hitting the true length, and then going radial. The center hitting the true length and going radial. So we are sure that the distances here are accurate. You can actually check that from PO to PO. Let's see. And we have 33 right there. Just wanted to show you something. And then we have from 0 to 0 also showing that it is 33. So we are correct in this regard. The next challenge is getting this point P2, P1, intersecting the corresponding lines. To do that, you take your compass, not that too difficult, it's easy. Starting from PO and P0, they're all in the same axis already, so we'll go straight to P1. The first P1 from the top, first P1 from the top. Take your arc, sitting on 0 as reference, and then extend it to 1. I have 14.11, all right. 14.11, you transfer that arc on P1 from the top and go this way, 14.11. Create your arc. All right. You go back same way. This time around, sitting on the same line, position 2. Yeah, I'm on 2 now. I'll sit on position 2, corresponding to 0 position as my reference. 0 is always my reference. Then I extend my arc to P2 right here. Let's zoom it out. From 0 to P2, 16.4. Go back to the development, sit on C2, extend that same arc, okay, 16.4, and cut your arc. That method is going to be approximate. You do the same thing sitting on the last one. The last P1 at the bottom, sit on 0, again, sit on 0, and then extend to 1. I have 10.9. Go back to the bottom line, the bottom one PO, trace PO right here, P1 here, and then I sit on the center point 0 of that same line 1 and extend 10.9. Okay, I create an arc. Now after that, you draw a smooth curve starting from this point, connecting to 1, 2, back to 1, 0, until you join all the points to get the shape that is out here. Thank you.